Hi everyone, in this video for 163.14 combinatorics we're going to look at selections, ordered, unordered, and with and without replacement. Okay, and so at the end of it we'll have the theory we need to answer these three questions here. Okay, so the setup is that I'm travelling in Italy and I want to send a postcard home to each of my friends Adam, Bella, Carl and Delia. And the post office sells 10 different postcards. Okay, so let's look at each question in turn. So in the first one, there's an unlimited supply of each card, and we want to know how many ways are there to send a postcard to each of my 4 friends. Alright, so let's just think about what we need to do. We need to choose 4 postcards, one for each of my 4 friends, and we've got 10 options to choose from. Now there's an unlimited supply of each card, so we can choose the same card more than once. And the order matters because Adam is going to think it's a different outcome if he gets the one of the castle compared to the one of the fountain. Okay, so the order in which I choose the cards matters. Okay, so this is a case of ordered selection. Okay, the order matters here. And it's with replacement because I can choose the same card more than once. Okay, and we want to choose 4 things from 10 here. Okay, so that's what we want to do. So, so there's a theorem that tells us the number of ways to do that, and that's this one here. So the ordered selection with replacement. The number of ordered selections with replacement of k objects from a set of cardinality n is n to the k. Okay, so what we're going to do is we want to prove this theorem, and I guess in the problem. So we said that was ordered selection with a replacement, and we had n is equal to 10 and k is equal to 4, right? So this is we're choosing k things, choosing 4 things, and we've got 10 options. And so the answer will be 10 to the 4. Okay, so why do we get this result that it's n to the k? Let's just recall our multiplication principle. So it says if an outcome is the result of a series of n choices, and there are ti options at step I, and the number of possible outcomes is just the product of the number of options at each step. Okay, so the way that we could think about choosing these postcards is we could write down 4 boxes, so this is going to correspond to the 4 friends, and then just inside each box we'll write which postcard we get for them. So from there's 10 postcards, so maybe I choose the 7th one for Adam, and then the 3rd one for Bella, because I know she likes fountains, so I'll get her the one with the fountain. And then I also send postcard 7 to Carl, and then postcard 2 for Delia. So that's sort of the process we could go through, and so of choosing the postcards, and so we made a series of 4 choices, and at each step, so n was 4 here, and so we had 10 options at each step. So T1 was equal to T2 was equal to T3 was equal to T4. Okay, and so our answer was equal to 10. Okay, and so we just multiply all those t's, and so we get 10 to the 4. Okay, so that's sort of what we do in general. Right, we'll have k boxes, and we've got n options at each step. So we're going to have k choices, and ti is going to equal n for each i. Okay, and so then we're just going to multiply all those together, and we'll end up with the product of the ti's will be n to the k. Okay, so that's ordered selection with replacement, and we've answered that first question, right? So the answer here, which side it was 10 to the 4. Alright, so let's move on to the second question. So now it says there's only one of each card, so we want to know how many ways are there to send the cards now. Okay, so this is still going to be an ordered selection. Oops. And limit of 4 objects from 10. Right, so again we've got there's 10 possible postcards and we've got to choose 4 of them, and so it's an ordered selection, and because there's only one, this is selection without replacement, because we can't choose the same card twice. Alright, so the theory for that, for ordered selection without replacement, so the number of ordered selections without replacement of k objects from a set of cardinality n is n times n minus 1 times n minus 2 times dot 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 down to times n minus k plus 1. And we can express that as n factorial over n minus k factorial. So for the problem, let's just see why we get this answer. So we're going to use the multiplication principle again. So I've got 4 boxes, and I'm going to write my choice of postcard in each one. So maybe I choose the 7th postcard for the first one. And so we had 10 choices here. And then at the second step, I've already chosen the 7th postcard. There's no longer one available, so I have to choose something different there. So maybe again I choose the 3rd one. But we only had 9 choices this time. And then, so now 7 and 3 are gone. So we've only got 8 options there. I can't choose 7 again like I did last time, so maybe I have to choose 6 instead. And so we had 8 choices, and then we've used up 3, and so we've got 7 choices left. Okay, so here, just with respect to our multiplication principle, we had 4 steps, and T1 was equal to 10, T2 was equal to 9, T3 was equal to 8, and T4 was equal to 7. Okay, and so then we get the product. It's going to be 10 times 9 times 8 times 7. Okay, so just and that's how this works in general. We've got our K boxes. This time I'm going to write the number of options in each box. So I've got n options here, and then I've used up 1, so I've just got n minus 1 left here, then n minus 2, and you can check that at the end we've got n minus k plus 1 options left at that last step, and so that gives us this product here as the answer. Right, and so just remembering that the n factorial is the product of all the integers from n to 1. Right, we can think of this as, so this is basically n factorial, but then we divide by the product of n minus k factorial. So that's another way to express it. And just as the special case of this, so if we actually choose all n elements, then that gives us the number of possible orders of a set of n elements. So we're going to if we choose all of them, we get the number of ways to do that is n factorial, which is n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So that's the number of possible orders of a set of n elements. And we can see that up in here. So we need to get n factorial over n minus n factorial, so that's n factorial over 0 factorial. And we want to remember that 0 factorial is defined to equal 1. Okay, and that makes sense because 0 factorial should be the number of possible orders of a set of 0 elements, and there's only one way to order to 0 elements, and that's this order right here, where we don't write any of them down. So there's one way to order 0 elements, so this makes sense to say that 0 factorial is 1. Okay, so going back to here, our answer is 10 factorial over 10 minus 4 factorial. So that's 10 factorial over 6 factorial, which is 10 times 9 times 8 times 7. And so either of these two would be perfectly correct, perfectly fine as an answer. Alright, so finally, there's only one of each card, and I'm in a rush. So I'm just going to buy the 4 cards now, and later on I'll decide who's going to get which of the 4 cards I get. So now how many ways are there to choose the 4 cards to buy? Okay, so again, we want to choose 4 cards from 10. And there's only one, so it's without replacement again. I just forgot to write that up here. This was without replacement. This one is also without replacement. And the order doesn't matter, because I'm going to figure out who gets which card later. Okay, so this is going to be an unordered selection. Right, basically I'm going to order them later on. Okay, so what's the theory for that? So here it is here. So the number of unordered selections without replacement of k objects from a set of size n is given by what's called the binomial coefficient. So the symbol here, we read that as n choose k, and it's equal to n factorial over k factorial times n minus k factorial. Okay, so let's convince ourselves that this is true. So in order to do this, we're going to give ourselves a process for choosing those k objects. So what I'm going to do is I'm going to write down some boxes like I always do, and I'm going to have k here. Then I'm going to draw a line, and I'm going to draw another n minus k boxes. Okay, so altogether I've got n boxes here. So just to give ourselves a concrete example, let's say n is equal to 7 and k is equal to 3. So I'm going to write down 3 boxes and then another 4. Right, so altogether I've got 7 boxes. Right, so I've got 3 and 4, and together that adds up to 7. Okay, so let's just pretend we're going to, well, let's come back up here. So what I'm going to do is I'm actually going to fill in each of these boxes with all n of my objects, right? So I'm going to fill them in. So without replacement, I'm going to put an object into each of these boxes using up all n objects. So if I just say over here, maybe my set is 1 to 7. So I'm going to fill these boxes in with 1 to 7. So I might have, say, 2, 4, 7, 6, 1, 5, and 3. Alright, so I filled in these boxes. And then I'm going to take those first 3 as my choice. Right, so we choose 2, 4, and 7. Okay, so that's what happens over here. We put the n objects into our boxes, and then we just take the first k, and those are the ones that we choose. Right. So we want to use this to figure out this value here. So we want to think about how many ways there are to fill in these boxes. Well, we just saw a little earlier that there's n factorial order, different orders to fill in these boxes. So we're going to have 7 factorial possible orders right here. And over here we'll have n factorial possible orders. Okay, so that's the number of ways in which I could fill in the boxes. So then the question is, how many times do I choose 2, 4, 7? Okay, so how many ways can I get 2, 4, 7? Well, so the process here, I need to write, so first I need to write 2, 4, and 7 in these 3 boxes in some order. Okay, and so there's 3 factorial orders for 2, 4, and 7 in those first boxes. And then I also need to write 6, 1, 5, and 3 in these boxes in some order. Okay, and there's 4 factorial ways to do that. So there's 4 factorial orders for 1, 3, 5, and 6. Okay, and so any one of those orders for 2, 4, and 7, followed by any one of those orders for 1, 3, 5, and 6, will give me the same outcome of choosing 2, 4, and 7. Okay, and so our multiplication principle tells us that like if I'm going to choose 2, 4, and 7, well, I had 3 factorial ways to fill in this first part. So that's at my first step, I've got 3 factorial options for how to do it. And then at my second step of filling in here, I've got 4 factorial ways in which to do that. So what we get is that there's 3 factorial times 4 factorial ways to get 2, 4, and 7. Okay, and just in sort of coming back over to the more general situation. So given a choice of k objects in the first box, k boxes, there's sort of k factorial ways to fill in the first k boxes with that choice of k objects, and then there's n minus k factorial ways to fill in sort of the last n minus k boxes. Okay, so the choice occurs k factorial times n minus k factorial times. So I've run out of room on my piece of paper really, but so there's n factorial possible orders, and each of the outcomes, each of the choices of k objects occurs this many times. So the total number of so what that tells us is that k factorial times the n minus k factorial times n choose k. Right. So this is the number of possible. This is the number of ways to choose our k objects, and this is the number of times each choice occurs. So that has to equal the n factorial. And so if we just divide, we end up with a formula right here. Okay. So that's how we can derive this formula for unordered selection without replacement. Okay, so if we go back to our problem. Right, so the answer is 10 choose 4. So that's 10 factorial over 4 factorial times 6 factorial. Okay, so that's our answer there. Okay, so that's how to that's the theory behind selections, so ordered and unordered, with and without replacement, and examples of how to solve, I guess, recognize those types of problems and solve them. Now you might have noticed that this actually gives us 4 possibilities, right? So, and the one we haven't talked about, I think, is unordered selections with replacement. Okay, so that'll be the subject of another video. All right, so till then.